Hi everyone, welcome to the Unit 4.2 review video. Let's go ahead and get started. The first set of directions ask us to express each exponential equation as a logarithmic equation. And the way we do that is doing something called the log roll. And the way we log roll is we always start with our base, which in problem number 1 is 3. And we start and then we pick up the 8 and then go from the 8 to the x. And we write our answer as log base 3 of 8 equals x. Okay, now let's do the same thing with number 2. We start off with our base of 3, roll over to the 27, and then from the 27 back up to the exponent of 3. And we write it as log base 3 of 27 equals 3. Okay, on problem number 3, we start off with our base of 2. We pick up 16 and then go from 16 to the exponent of 2x. And we write it as log base 2 of 16 equals 2x. In problem 4, we start off with the base of 6, pick up 216, and go from 216 to 3. So we write it as log base 6 of 216 equals 3. On problem 5, we start off with our base of 2, pick up the 32, and go from 32 to x. And we write our answer as log base 2 of 32 equals x. In question number 6, our base is 9. We pick up the 729, and then from the 729 we go back up to the 3. So we write it as log base 9 of 729 equals 3. Okay, now in the second set of directions, they ask us to express each logarithmic equation as an exponential equation. So we're doing the opposite this time, but the process is still the same. We're going to do the log roll. But we start off with our base, which in these logarithmic equations is the smaller number right next to the word log. So in problem 7, our base is 8. We go to the x, and then from the x we go back up to the 3. So our answer becomes 8 raised to the x equals 3. Okay, in problem 8, we start off with our base of 8, pick up the 1, and then go from 1 back to the 8, and we write our exponential equation as 8 raised to the first power equals 8. Problem 9, we start off with our base of 4, pick up the 3 halves, and then back to the larger 8, and the way we write it is 4 raised to the 3 halves equals 8. Okay, in problem 10, we start off with our base of 7, pick up the 2, the exponent of 2, and then go over to the 49. And so we write it as 7 squared equals 49. Okay, in problem 11, we start off with the base of 2, pick up the x, and go to 32. So we write it as 2 raised to the x equals 32. In problem 12, we start off with the base of 4, pick up the x, and then go to the 1/2, and we write it as 4 raised to the x equals 1/2. Okay, now the next set of directions ask us to use mental math to evaluate each logarithm. So, remember in problem 13, there's no base to this logarithm. So we have to remember our common logarithm is log base 10. So if you see something written without a base, we assume that it's log base 10. So 13 can be written as log base 10 of 1. And the way we evaluate this is we think of the exponent that we could raise 10 to equal 1. So 10 raised to an exponent has to equal 1, and we are interested in that exponent. And that exponent is going to be 0. Okay? In problem 4, it's the same situation. We have to look at what we could raise our base to, which here is 5, to give us 5. So 5 raised to the first power gives us 5. So log base 5 of 5 is equal to 1. In number 15, we look at what power we could raise our base of 6 to give us 36. And we know that 6 squared equals 36. So the power log base 6 of 36 is equal to 2. Okay, in problem 16, we notice that there's no base, so we have to assume that it's log base 10 of 10. And once again, if you look up at 14, when your base is equal to the number, here the log was 1. Here it's the same situation, so 10 raised to the first power is going to give you 10. So our answer to number 16 is 1. Log 10 is 1. Okay, in number 17, we think of the power that we can raise 8 to give us 1, and it is 0. 8 raised to the 0 power is equal to 1, so log base 8 of 1 is 0. Log base 14 of 16 is going to be 2, because if you think about it, 4 squared gives you 16. In the next section, we're identifying these functions as either exponential growth or decay. And the function that we know as the exponential function is f of x equals b raised to the x. And if b is greater than 1, then we're dealing with growth, exponential growth. And if b is less than 1, we're dealing with exponential decay. So, in problem 19, our b value is 0.2. Therefore, it's less than 1. So 19 is an exponential decay function. In 20, our b value is 8, so it's greater than 1, so we are dealing with exponential growth. In 21, our value is 4/5, and 4/5 is less than 1, therefore we're dealing with decay. In the second problem, 21, our b value is 17.1, so we are dealing with growth because 17.1 is greater than 1. Here, our b value is 1.2, which is greater than 1, so 22 is growth. On 23, 3/2 is actually greater than 1. Don't let the fraction fool you. I think sometimes y'all look at fractions as automatically being less than 1, but sometimes they're greater than 1. So 3/2 is greater than 1, so 23 is an exponential growth function. In the next section of our review, we're given some formulas that deal with exponential growth and decay in terms of application problems. The first formula they give us is A equals P times 1 plus R raised to the T. And we're going to use this formula when we have growth, exponential growth. And when we have exponential decay, we will use the formula A equals P times 1 minus R raised to the T. And when we have compound interest problems, we're going to use the formula A equals P times 1 plus R over N raised to the N times T. So let's look at problem 24. Jared decides to invest $5,600 at an annual rate of 8.23% at Capital One Bank. When someone invests money and earns interest on that money they've invested, that is an exponential growth. So we are going to use the first formula that they gave us, which is A equals P times 1 plus R raised to the T. So when we're looking for what these letters mean, P is the initial amount that we start with, which is $5,600. So P is going to be equal to $5,600. R is the rate at which we are increasing or decreasing. We already know that it's an increase in this case, but our R value is 8.23%, and we changed that to a decimal to be 0.0823. To convert a percent to a decimal, remember we just moved the decimal over 2 times to the left. Okay, so now we just plug in, because part A is asking us to write an equation that represents the money in Jared's account at time t. So, the amount in Jared's account is equal to $5,600 times 1 plus R. So 1 plus 0.0823 is 1.0823 raised to the T. So now we have an equation to where we just plug in the number of years and we'll be able to find the amount of money in Jared's account. In part B, they ask us after 3 years, how much money does Jared have in the bank? So this just tells us that T is equal to 3. So we're going to plug into our calculator A equals 5,600 times 1.0823 raised to the third power. And when we type that into our calculator, it should give us $7,099.55. So after 3 years, that's the amount of money he'll have in his account. On problem 25, it says Claire bought her first sports car 3 years ago for $21,500. She read in a magazine that her car's value will decrease by 5.3% each year. So this word decrease tells us which formula to use, which is the decay formula up at the top that they've given us. So we're going to write it as A equals P times 1 minus R raised to the T. The initial amount that she starts with, P, is $21,500. And the rate at which it's decreasing is 5.3%. And we write that as a decimal as 0.053. Okay, so now we're just going to plug that in because part A asks us to write an equation that represents the value of Claire's car at time T. So the amount of her car is equal to $21,500 times 1 minus 0.053, which is equal to 0.947 raised to the T. Okay, it's asking what is Claire's car worth today? Well, she bought it 3 years ago. Today, the T value is 3. So 3 years have passed. So we plug 3 in for our function where we see T. And when you plug that formula into our function, or into our calculator, I apologize, it ends up giving you $18,259.50. Okay? Alright, in part C, they're asking us what will the car be worth after 2 more years? So, if it's already been 3 years, and then we add 2 more years onto that, our T value is now 5. So we do the same thing as in part B, except our T value is 5 instead of 3. Plug it into your calculator, and you should end up getting $16,375.30. Okay, problem 26 says at 12 noon, there are 225 bacteria in a petri dish, and the bacteria triple every minute. So, we are using the exponential growth function in this case because the number of bacteria is growing. So we're using A equals P times 1 plus R raised to the T. Our P value is 225 because we start off with 225 bacteria. And the rate at which it's increasing is 200%. When something triples, it's increasing by 200%. So we write that as 2. We change the percentage to just a numerical value of 2. And the way we're going to write our formula or equation is A equals 225. 1 plus R is 3. 1 plus 2 is 3 raised to the T. And it's asking us after 13 minutes how many bacteria are in the petri dish. So our T value in this case is 13. So A equals 225 times 3 raised to the 13th power. And this gives us, when we plug into our calculator, a value of 358,722,675. It's amazing how much bacteria grew in 13 minutes, right? 7, they say a painting is worth $1,000 and the value of the painting has been increasing at 8.2% each year for 10 years. And they want an equation to represent the original amount of the painting P. So since it's increasing, the value of the painting is increasing, we know we're going to use the formula A equals P times 1 plus R raised to the T. Now we know what A is. The amount of the painting right now is $1,000. In R, the rate at which it's increasing is 8.2%, or in decimal form, 0.082. And our T value is 10. It's been increasing for 10 years. So, if we were to write it, I would write it as $1,000, the amount the painting's originally worth, is equal to the original amount times 1.082. 1 plus r is 1 plus 0.082 raised to the 10th power. In part B, they ask us how much the painting is originally worth. So we're going to go to our calculator, and what we're going to enter to solve for P, we're going to take 1,000 and divide it by 1.082 raised to the 10th power. So in our calculator, 1,000 divided by 1.082 raised to the 10th power is 454.703, or in a dollar amount, it's $454.70. So the painting was originally worth $454.70. Problem number 28 says a house is initially valued at $150,000 and is decreasing at 5.75% each year. So we're going to go ahead and use the decay function, which is A equals P times 1 minus R raised to the T. And they ask us to write an equation to represent the house at time T. The initial amount, P, of the house is $150,000. The rate at which the value is decreasing is 5.75%, or in decimal form, 0.0575. And we're going to go ahead and we can now fill in that the amount of the house equals the initial amount of $155,000 times 1 minus 0.0575, which is 0.9425 raised to the T. Okay, 29. It says a company doubles in size each year from an initial size of 12 people. So we're using the exponential growth function, A equals P times 1 plus R raised to the T. The initial amount of people is 12. The rate at which it's increasing, it says it doubles in size, so that means it increases by 100% each year. So changing that 100% to a decimal is just 1. So when it asks us to write an equation to represent the number of people in the company at time T, we write it as A, the amount of people, equals the initial amount, 12, times 1 plus R, which in this case is 1 plus 1. So 12 times 2 raised to the T. In part B, they ask us how many people will there be in the company after 5 years. So the amount of people equals 12 times 2 raised to the 5th power. When we enter that into our calculator, it tells us there's going to be 384 people in the company after 5 years. In problem 30, they tell us $800 is deposited into an account that pays 9% annual interest. Find the following amounts. So the part A asks us for 8 years compounded quarterly. That word compounded tells me I'm going to be using the compound interest formula, which is A equals P times 1 plus R over N times N to the T. So we know that the initial amount deposited is $800. The rate at which it's increasing each annual interest is 9%, or in decimal form 0.09. And in part A, they tell us that it's for 8 years. So our T value is 8. And since it's compounded quarterly, N is equal to the number of times each year it's compounded. So quarterly means it's compounded 4 times each year. So when we plug in, we get A equals the initial amount, $800, times 1 plus the rate, 0.09, over N, 4, raised to the N times T, which in this case is 4 times 8. When you type that into your calculator, you end up getting $1,630.48. In part B, we're going to use the same P and R value, but our T and N value change. Because now we're talking about the same bank account, but for 7 years compounded monthly. So the T value here is going to be 7. And there's 12 months in a year, so it's compounded 12 times each year. So our formula is A equals 800 times 1 plus 0.09 over 12 times, or raised to the 12 times 7. And when you enter that into your calculator, you end up getting $1,498.56. In part C, they want to know how much money is in the account after 6 years if it's compounded weekly. So our T value here is 6. And if it's compounded weekly, that means it's going to be compounded 52 times in a year. So N is equal to 52. So A equals 800 times 1 plus 0.09 over 52 raised to 6 times 52. After entering that into your calculator, you should get $1,372.16. In part D, it's asking how much is going to be in the account after 9 years compounded annually. So our T value is 9, and if it's compounded annually, that means it gets compounded once a year. So A equals 800 times 1 plus 0.09 over 1 raised to 9 times 1. And after entering that into your calculator, you end up getting $1,737.51. In problem 31, they ask us what would the original investment have to be to earn $10,000. And it's the same as in problem 30 where they give us years and how much it's compounded each year. So we're going to still be dealing with the compound interest formula, which is A equals P times 1 plus R over N raised to the N times T. And they tell us in this case how much money is earned already. So our A value, they tell us, has to be $10,000. And we're still going to use the same rate as in problem 30. The rate is 9%. But we changed that to a decimal form to be 0.09. And we are going to be looking for our P value. That's what we're going to be looking for in these problems. In part A, they ask us for 4 years compounded quarterly. How much would have to be invested? Well, that means our T value is 4. And since it's compounded quarterly, it's compounded 4 times a year. So we plug in our values into our formula. And we get 10,000 equals P, what we're looking for, times 1 plus 0.09 over 4 raised to the 4 times 4. And when you enter that in your calculator, you should enter it as 10,000 divided by 1 plus, and then to enter a fraction, you hit Control Divide, 0.09 over 4, raised, to enter an exponent, you enter this little caret next to the x squared button, the 4 times 4. And when you enter, you get your initial value as $7,004.66. Okay, in part B, it says for 5 years compounded monthly. So our T value is 5, and there's 12 months in years, so it's compounded 12 times, and N is equal to 12. Our formula becomes 10,000 equals P times 1 plus 0.09 over 12 raised to the 5 times 12. When we enter that into our calculator, we get 10,000 divided by 1 plus, control divide for a fraction, 0.09 divided by 12. Get outside of the parentheses using the right arrow button. Use the little caret button to get an exponent, and it's 5 times 12. Whoops, hit the wrong button. 5 times 12. And you should get $6,387 as your initial amount invested. Okay, in part C, our T value is 6, and it's compounded weekly, so N is going to be 52 since there's 52 weeks in a year. So our formula is 10,000 equals P times 1 plus 0.09 over 52 raised to the 6 times 52. And when you enter that into your calculator and solve for P, you end up with $5,830.20. In part D, it says for 7 years compounded annually. So T is 7 and N is going to be annually, so 1 time a year it gets compounded. So 10,000 equals P times 1 plus 0.09 over 1 times 1 times 7, raised to the 1 times 7. And when you enter that into your calculator, you should get $5,470.34. Alright, so now we're moving on to the graphing problems. And it asks us to graph the following and give the domain, range, and equation of the asymptote. So, in these graphing problems, we're going to be dealing with 4 different functions. We're dealing with the 2 parent exponential functions and the 2 parent logarithmic functions. The 2 parent exponential functions are f of x equals 2 raised to the x, and f of x equals 1/2 raised to the x. And the parent logarithmic functions are f of x equals log base 2 of x, and f of x equals log base 1/2 of x. So once you look at these functions given to you, you're going to have to determine which parent function they come from. And after that, then you can apply your transformations and be good to go. So let's look at problem 32. The equation is f of x equals -2 raised to the x plus 3 plus 3. Well, the parent function we're dealing with here is f of x equals 2 raised to the x. It's an exponential parent function. And when we plot those parent points, and you're going to have to remember in those parent points, okay, that's what you're going to have to remember. After this, it's just simply transformations that we're going to be dealing with. So I plotted my parent points. Now let's talk about what transformations is going to make to those points. Remember, we deal with left and right first, and here we have x plus 3 in the exponent, so that means I'm going to be moving left 3. Then we deal with reflections, and this negative out in front tells me that I'm going to reflect over the x-axis. And then this plus 3 in the back means I'm going to move up 3. So I start at any point, and I move left 3, reflect over the x-axis, meaning, so if I started with this point right here and I moved left 3, then I'd end up at -2, 2. When I reflect it over the x-axis, I end up at -2, -2. And then I move up 3 from there, and this is the new point that I get. And I go ahead and do that with all of my points. So I'm going to go ahead and do that, and go ahead and you do that on your worksheet too. Okay, and your parent function should end up looking, I messed up on mine, something of this sort. Okay? And if you notice, the graph is approaching this line right here, but it will never actually touch it. So, if a line that a graph approaches but never touches is called the asymptote. So the equation of our asymptote here is y equals 3. Okay, in our domain are all of our x values, and it's going to actually encompass all x values because it's going to keep extending left and right forever. So in interval notation, that's from negative infinity to infinity. In our range are our y values, and all of our y values are less than 3 in this case. Okay, moving on to 33. The parent function we're dealing with here is f of x equals 1/2 raised to the x. And when we plot those points, you should end up getting something that, parent points, you should end up getting something that looks like this. Okay, and now we're going to look at the transformations that need to be made. We look at left, right first, and this x plus 2 tells me I'm moving left 2. There's no reflections in this problem, and this negative 2 out in the back tells me I'm moving down 2. So we're moving each point to the left 2 and down 2. Okay, and when you connect those points, your graph should end up looking like this. Okay, our domain is all real numbers because it's going to encompass all x values from negative infinity to infinity. And our y values all must be greater than negative 2. So, our asymptote is a line that the graph never touches, but it approaches, and that, in this case, the equation of that line is y equals negative 2. The graph will approach y equals negative 2 but never touch it. Okay, in 34, the parent function that we're dealing with is f of x equals log base 2 to the x. So I'm going to go ahead and plot those parent points for that function. And if you need to memorize those, refer back to those worksheets we did in class. That will help you. Okay, and the transformations with the x, we move left and right. So this tells me the plus 3 inside with the x tells me I need to move left 3. And this negative 5 out front means I need to move down 5. So I start at each point, move left 3, and then down 5. Connect those points, and your graph should look something like that. Now, my domain, if you notice, all of my x values are going to be greater than negative 3. All of my x values are greater than negative 3. And all of my y values, it's going to keep expanding, so it will encompass every y value if you were to extend this graph out. In an interval notation, you could write those as negative 3 to infinity or negative infinity to infinity for the domain and range. I will accept either as an answer. Okay, so now we're going to look at the asymptote. So we look at the line that the graph is approaching but never touches. And that's going to be the line, this vertical line right here that the line is approaching but will never touch, which is x equals negative 3. Okay, now moving on to 35. It tells us f of x equals negative log 1/2 of x minus 2. The parent function we're dealing with is f of x equals log 1/2 of x. So we're going to plot those points, those parent points first, and then we'll apply our transformations. Now looking at the transformations we're going to apply to this graph, this -2 inside with the x tells me I'm going to move right 2, and this negative out front means I'm going to reflect over the x-axis. So I take each point, I move right 2, and then reflect over the x-axis. Okay, and when you've graphed that, you realize that your domain, all of your x values are greater than 2, and your range is all real numbers, and those in interval notation are 2 to infinity or -infinity to infinity. And the line that it will never touch but it keeps approaching is x equals 2. Alright, number 36, the parent function we're dealing with is f of x equals 2 raised to the x. And the parent points for that function are as follows. And we are going to, what it's asking us to do, the transformations that we're going to apply, the x minus 3 in the exponent tells me I'm going to move right 3 and down 2. So, I take each point, move it right 3 and down 2. Connect those points. And your domain is going to be all real numbers, -infinity to infinity. Your range, all of your y values are greater than -2. And the asymptote, the line that the graph approaches but will never touch, is y equals -2. In problem 37, we have f of x equals -1/2 raised to the x minus 3 plus 4. And our parent function is going to be f of x equals 1/2 raised to the x. So we plot those parent points, and once again, if you need to remember what those are, go refer back and study those worksheets that we did in class over sections 7.1 and 7.3. Okay, and the transformations that we need to apply, we look left, right first, so that we look at the x's and we know we're going to move right 3. We then reflect, and our reflection is in the negative out front. So we reflect over the x-axis. And then this plus 4 means we're going to move up 4. So remember, you look right, left, then reflect, then up, down. And we're going to apply those to each of these points. And once you're done plotting, it should look something like that. And you realize that your x values, or your domain, is all real numbers from -infinity to infinity. Your range, all of your y values, must be less than 4. So y must be less than 4. And the asymptote, that the line that your graph is approaching but will never touch, is the equation of that line is y equals 4. Okay, 38. The parent function we're dealing with here is f of x equals log base 2 of x. So we plot those points. And then we need to look at our transformations. We look left, right first. And x minus 3 tells me I'm moving right 3. This negative out front tells me I'm reflecting over the x-axis. And this positive 2 means I'm moving up 2. So, we do that to each one of those points. And if your points end up going off the graph, that's okay. Just do what you can. Okay, and that's what your new graph should look like. And your domain, all of your x values must be greater than 3. And your range is all real numbers. So in interval notation, your domain is 3, infinity. And your range is negative infinity to positive infinity. The asymptote, the line in which your graph will never touch, the equation for that is x equals 3. Okay, moving on to 39. The parent function that we're dealing with here is f of x equals log base 1/2 x. So when we plot those points, they should look like that. And the transformations we're applying, left, right first. This tells me we're moving left 4. And this positive in front of the log means we're not reflecting anywhere. We're okay. We're good to go. And this minus 1 tells me I'm moving down 1. Okay, so I take each point, move it left 4, down 1. Connect your points. And you should realize that your domain, all of your x values must be greater than -4. Your range is all real numbers. If you write those in interval notations, it's -4, infinity, and negative infinity to infinity. And the equation of your asymptote, the line that it approaches but will never touch, is x equals -4. Okay, y'all, that's the end of the review video, and I hope that y'all study it. Let us know if you have any questions in the morning, and good luck on your test.